Hello everyone, my name is Kanstantsin Moiski. I have over 8 years of experience as software developer with a strong focus on Java-related technologies. My professional interests include distributed system, performance optimization, and fault tolerance. Today, I would like to talk to you about our search engine. Let's go. Let's dive in. I will simplify complex concepts and I have slides to help explain and illustrate these ideas. Before we get into the search engine, let me explain our architecture. It's built around two main abstractions, Edge and Hive. Hive acts as a central data center where data from the Edge converges. It handles the processing, management, and storage of events with the search engine as core component. Edge, in this context, working as small and remote data center, its main tasks include receiving events from data sources, storing some data in blob storage, processing events, and transmitting them to Hive. You can think of Hive as a beehive and H as trees or plants. Bees collect pollen from plants or trees and bring it to the hive. In the same way, H collects data and sends it to Hive. We use Apache Ignite as our search engine. Let me walk you through the search request flow. In the first, the user sends a search request with the proxy through Nginx. Next, the request is passed to a microservice called HAPI, which handles validation, post-processing, and business logic. After that, the request is sent to a microservice called Event Search Manager, where the request is registered and assigned a unique ID. After that, registration details sent to a Kafka topic. A microservice called SSE holder consumes records from this topic, processes them, and notifies user via server-sent events. This non-blocking mechanism lets user continue working while their query is processed. If you look at this slide, Event Search Manager places search queries in a search queue. We also track active search queries per user, and we use Ignite Search Semaphore to prevent users from sending multiple parallel requests simultaneously. Queries are processed and sent to Event Search, which communicates with Apache Ignite to retrieve results. After that, results are sent back to Event Search Manager, where they are saved in Apache Cassandra. After the search request has been completed, the notification is sent to Apache Kafka, and our service SSE holder informs the user. Where is the problem? You ask me. I don't see any problem here. It's working. It's working. One day, we used Grafana to analyze metrics in one of our production cluster. We find that we have two types of queries, slow and fast queries. Slow queries, represented in yellow on this slide, took significantly longer to complete. On the other hand, fast queries, shown in green, were executed quickly. Okay, I have only one question. How much data is stored in Apache Ignite cluster? The dataset in Apache Ignite cluster contains more than 2 billion records. Okay, I think we have a time to investigate and analyze what is happening in our search engine. We have two types of queries, fast and slow queries. Okay, let's dive deeper into what slow queries. What is happening here? For instance, this slide represents how we can build search requests. The number of possible filter combination is calculated as 2 raised to the power of n. For this search page, the number of possible filter combination variation is more than 8,000. The worst case scenario, a case when the data corresponding to the filter does not exist in our system. And this requires a search across all events within the entire 30-day window. It's full scan. It's an harmful situation. It's a bad situation. It's a scary situation. Do you know how to optimize our search request so that it runs faster? Okay, we can use indexes, such as, for example, single column indexes, composite indexes, or covering indexes. Let's talk about single column indexes and their role in optimizing search performance. Single column indexes are created on frequently queried columns. On this slide, we explore the advantages and disadvantages of using single column indexes. The key takeaway is that single column indexes are ideal for specific scenarios. However, for complex queries involving multiple filtering conditions, composite or covering indexes may be a better choice. Now, let's dive into composite indexes and when to use them. Composite indexes are designed for queries that filter by multiple columns. By creating index on both columns, you can optimize these types of queries. On this slide, we explore the advantages and disadvantages. We have a pros and cons of using composite indexes. In summary, composite indexes are ideal for multi-column queries. However, it's important to consider storage requirements and index structure to ensure optimal performance. Next, let's explore covering indexes and how they can enhance our search performance. Covering indexes include all the columns used in a query, so they can avoid extra lookouts by storing all the necessary data in the index itself. On this slide, we explore the pros and cons of using covering indexes. In conclusion, covering indexes are powerful for optimizing specific queries, but make sure they align with your data access patterns to avoid unnecessary overhead. When you use indexes, please be careful to avoid the following situations. Okay, what else can I do? Let's talk about partition data and its importance for optimizing performance. Data partitioning is a strategy that ensures related data is stored together, making it easier to access and manage. By partitioning your data, you can improve query performance, especially when dealing with large datasets. This approach ensures that related data is physically stored together, reducing the time it takes to retrieve it. Okay, what else can I do? Now, let's discuss the importance of using filtering as a source to optimize data retrieval. By applying filters directly in your query, such as time range, just like event time or specific sources like channel ID, you can limit the amount of data fetched, significantly improving performance. A key point to remember is that columns used by filtering should be indexed. This ensures that filtering process is fast and efficient, minimizing unnecessary data retrieval. In summary, filtering at the source not only reduces the data load, but when combined with proper indexes, can make your queries much faster and more efficient. Okay, what else can I do? Next, let's explore the concept of using pre-aggregated data for optimizing performance. For repetitive query or analytics, pre-aggregation data into summary tables or materialized views can significantly reduce processing during runtime. By storing pre-aggregation results, you can speed up query response times and offload heavy processing tasks, making your application more efficient. In summary, pre-aggregation data is powerful technical to improve performance, especially for queries that need to process large datasets repeatedly. what do we use in our project? In our project, we use a combination of strategies to optimize performance. First, we leverage single column indexes to speed up queries that filter by a single column. These indexes ensure fast query execution while using minimal storage. Next, we partition our data to ensure that related data is stored together. This improves query performance by organizing the data in a way that makes it easier to access. Finally, we apply filtering at the source, limiting the data fetching by applying filters directly in the query. For example, we filter by time range and specific sources, and we ensure that the filter columns are indexed for optimal performance. Do you know how to avoid slow queries? Option number 1. If the code works, don't touch it. Option number 2. It's not my problem. It's not my problem. Option number 3. Imagine we use a next simple thread pool model to manage search requests efficiently. When a new search request arrives at our search engine, represented as new task on the slide, the query is placed into a queue. Next, the thread allocator identifies available thread to execute and task assigned to this thread for processing. Now, let's look at how the thread pool model works when we have only fast queries. In this scenario, we have task in our queue. The thread allocator assigns each task to an available thread for execution. Since the time to execute each task is quick, we can process incoming requests very efficiently. This ensures that our clients experience minimal wait times, as they don't have to wait long for response from our search engine. Now let's explore how the thread pool model works when we have mixed queries, such as fast and slow queries. In this scenario, we have six tasks in our queue. The thread allocator assigns 3 tasks to available thread for execution. In this slide, you can see that slow task is assigned to thread number 3. By managing both fast and slow tasks efficiently, we can ensure that quick tasks don't get delayed while still processing slower tasks in parallel. This approach allows us to optimize resource usage and provide timely responses for our clients, even when queries vary in complexity. Okay, let's look at the worst case scenario with both fast and slow queries. In this scenario, we have 3 slow tasks in our queue. The thread allocator assigns each slow task to available thread for execution. However, since all the threads are occupied with slow tasks, there are no available threads to process the incoming fast task. As a result, the fast tasks accumulate in the queue and have to wait until a thread becomes available to process them. This highlights a potential bottleneck in the system when slow task blocks fast task processing, leading to delay. This reminds us of line of people standing at the checkout to buy their items. It's an amazing picture. This situation is like a customer, for example, check at a checkout line buying a large number of items, for example, apples, causing delays for users. Do you know how to avoid slow queries? Optimization everywhere. We can use next interesting patterns such as query with narrow time windows. To optimize performance, avoid scanning large time ranges like an entire 30-day period if possible. Instead, use smaller time ranges for your queries and dynamically adjust the range if no results are found. This approach helps reduce the amount of data processing and speed up query execution, ensuring a more efficient and responsive system. Let's walk through the process when a request comes into our application, into our system. First, we register the incoming request in the microservice called Event Sort Manager and send it for processing in our thread pool model. If the next request is a slow query, what we take, what we're doing, sorry, we take an extra step. Instead of sending the entire query directly for execution, we break it down into smaller subqueries using narrow time windows. For example, we can define a one-day window unit. We then send the first subquery for execution in the thread pool. Once the first subquery is completed, we prepare the next subquery and send it for execution. This approach ensures that we only have fast queries running in our search engine at any given time and improving overall performance and responsiveness. What we have? We have equality. Maybe we have other benefits. To enhance user experience, we return search results to the user as soon as the first result is found. This approach reduces wait time and gives users immediate feedback while the remaining results continue to load. Imagine user sends a slow request. We handle it efficiently. We break it down into smaller subqueries using narrow time windows such as a one-day window unit. We send the first subquery for execution and quickly retrieve a result. Then we send the second subquery but find no results. Next we process the third subquery and retrieve another result. At this point, the user, for example, realizes they have gathered enough information and decides to cancel the slow request. This approach allows us to provide quick feedback to the user, ensuring they get relevant result faster while the rest of the query continues processing in smaller, manageable parts. Yes, we find a solution to resolve this situation. Thank you. See you later.